Recording in progress. Hello everyone, this is Sairaj from AML and my topic is Automata Modulo theories. What is automata theory? Study of abstract computing devices or machines. Automaton equal to an abstract computing device. A device need not even a physical hardware. It need not be a physical hardware. It may be a software also. A fundamental question in computer science: find out what different modules of machines can do and cannot do. The theory of competition, and there is a difference between computability and complexity. It will define the theory of competition. In mainly modulus theories, automaton modulus theories, it comes languages and grammars and strings and etc. We'll see in further. Now we'll discuss about language and grammars. Language is a collection of sentences of finite length, all constructed from a finite alphabet of symbols. Grammar is a grammar can be regarded as a device that enumerates the sentence of a language, nothing more, nothing less. An alphabet is a set of symbols. Here we can see these 0 and 1 are the alphabets or words. Sentences are strings of symbols. Here we can see there are more strings here. 0 is one string, 1 is one string, 0 0 is one string, 0 1 is one string, 1 0 is one string, and 1 and so on. A language is a set of sentences. Means here language consists of set of strings. We can call it as set of strings. So this set of strings is called the language. A grammar is a finite list of rules defines a language. Here, for example, this is a S, capital S and 0A. S defines the 0A. A defines the 1A. Here, grammar is a final list of rules. It defines a language, which is we can use this grammar to derive the strings, to get a language. This is the Chomsky hierarchy. We will see first regular DFA, definite finite automata, deterministic finite automata. In this next, context free grammar, PDA, push down automata, context sensitive LBA, recursively enumerable Turing machine. We'll use this recursive enumerable grammar in the Turing machine. We use regular grammar in the DFA, context free grammar in the PDA, context sensitive grammar is LBA. The central concepts of automated theory is first alphabets. Alphabets is a finite or non-set of symbols, non-empty set of symbols. That means it should contain at least one alphabet, one symbol. That is, we use the symbol sigma to denote an alphabet. We can clearly understand by using this example, binary. For example, binary means we'll get only zeros and ones. These zeros and ones are denoted in curly brackets by using the symbol sigma. In these, symbols should be all lowercase only. It should be lowercase in this. All lowercase letters are A, comma B, comma C up to Z. Alphanumeric. Alphanumeric means we'll get the alphabets and the numerics. Here we can say A to small z and capital A to capital Z and 0 to 9. DNA, molecule letters A, comma C, comma G, comma T. These are the examples of the alphabets. What is string? A string or what is a finite sequence of symbols chosen from symbol. That means empty string is epsilon. We can define empty string. That means there is no symbol. there is no symbol means we will define it as epsilon. Length of a string W denoted by mod W. For example, there is a string here, example mod x equals 6. That means x contain the six alphabets. Here we can see 0 is 1, 0, 1, 0, 1, 0, 0. These are 6 symbols. So this modulus x defines the length of the string. A length of a string W denoted by modulus x is equal to the number of non-epsilon characters in the string. Xy is the concatenation of two strings, x and y. That means, for example, x equal to 0, 1 and y equal to 1, 0. The concatenation of the x comma y is the 0, 1, 1, 0. Power of an alphabet. What is power of an alphabet? Alphabet means here we know that alphabet is denoted by sigma, and here the power of the alphabet is denoted by sigma power k. That means the k starts from defines the power of the alphabets, the set of all strings of length k. Here sigma star means sigma 0 union sigma 1 union sigma 2 union sigma 3 and infinity, up to infinity. Here sigma plus equal to sigma 1 union sigma 2 union sigma 3 union. The major difference between the sigma star and sigma plus is the sigma star contains the epsilon, that is empty string, and sigma plus includes the, it doesn't include the epsilon symbol. Language is said to be a language over alphabets only if L is subset of epsilon star. That means the language should contain the strings of epsilon from epsilon to infinity. This is because epsilon star is the set of all strings. This indicates the set of all strings of all possible length including 0. That is 0 means here epsilon over the given alphabet sigma. Example, let L be the language of all strings consisting of n zeros following by n ones. Here we can see n zeros or n ones. Here the main we have to identify, it should be first 0 should become, then after 1 should become. It should not be the combination of zeros and ones. It should be 1 should be followed by 0 only. The language is that, for that we will write here epsilon and 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1 and so on. And another example is, let L be the language of all strings of with equal number of zeros and equal number of ones. In these, it is different from first one because here 0 should be equal to the ones, 1 should be equal to the zeros. If 1 0 is there, and it must contain the 1 ones. Here we can see epsilon and 0 1 1 0 0 0 1 1 1 1 0 0. Here there is no mention 0 should be followed by 1 or 1 should be followed by 1. It is a combination of zeros and ones, but the rule is number of zeros is equal to number of ones. Definition: pi denotes the empty language. Here empty language is denoted by pi. The membership problem: given a string W belongs to epsilon star and a language L over sigma, decide whether or not W belongs to L. Here example, W equal to 1 0 0 0 1 1. Question is whether this string, the language of string with equal number of zeros and ones. Here it is asking that is it belongs to number of zeros equal to number of ones. Yes, we can say here there are 3 zeros and there are 3 ones, so we can say it is yes. These languages belongs, this string belongs to this language only. This is the called membership problem. Finite automata. What is finite automata? We'll see. Before that, we'll see what are applications of finite automata. Software applications for designing and checking the behavior of digital circuits. Lexical analyzer of a typical compiler. Software for scanning large bodies of text, example web pages for pattern finding. Software for verifying systems of all types that have a finite number of states, example stock market, transaction, communication network protocol. Finite automata example, if we take finite automata, in the generally finite automata contains the two types, deterministic finite automata and non-deterministic finite automata. We'll see the difference between deterministic and non-deterministic in the further. So let's understand this finite automata by using one example. On or off switch. This is the start symbol. This is the start state. Start state should be indicated by this arrow, and this is the transition. Here, if you want to go to off state to on state, we should push the switch. Then only action will be happen. This is the transition. If we want to go to off state to on state, we should push the switch. Then only action will be happen and it will move from off state to on state. If we want to move from on state to off state, it should be pushed. This is the finite automata, graphical representation of the finite automata. Modeling recognition of the word then. If we want the compiler should, if compiler wants to recognize, then it should be recognize first T, then H, then after E, then after N. The N should be ended with the final state. Then only it will recognize it as a word called then. First start, we know the start state should be indicated by arrow. Then from one state to another state T, then T state to T state H, then one state to another state E, this state to this state N. Here the N is completed with the final state. These are the intermediate state. We will call this arrow symbol is transition. This start state. This is the final state. So here the final state is recognized as N, last N. So we can say it is recognized and the word then is corrected. Structural expression. How we will express the words? We will see grammars. Regular expressions are expressed like, for example, unique style to capture city name such as Polo Alto CA. Here capital P, then after small letters there is space, and capital A and small letters there is space, then capital C, capital A. How we will represent these cities? How we will represent these sentences in the expressions? We will see. First there is a P, this is capital P, so we have represented it as capital A to Z. Then after capital small letters, then we will represent as small letters. Next star, this is star, and next to space, here we represented as space, and next capital A to Z, and small letters small a to Z, and the again space and capital A, capital C, capital A. Here space is represented by in this bracket space, and capital C is represented by capital A to Z, capital A represented by capital A to Z. Next, what is finite automata? Informally, a state diagram that comprehensively captures all possible states and transitions that a machine can take while responding to a stream or sequence of input symbols. Recognizer for regular languages. For these finite automata should recognize only the regular grammars only, regular languages only. There are two types of finite automata, deterministic finite automata and non-deterministic finite automata. What is deterministic? The machine can exist in only one state at any given time. What is non-deterministic? The machine can exist in multiple states at the same time. Deterministic finite automata is denoted by 5 symbols. That is Q. First capital Q. It is a set of states. A set of states. Symbol. A set of input symbols. Q naught is the initial state. F is the final state, and delta is the transition functions. Delta is the transition functions. A DFA is denoted by 5 tuple notation. These are the 5 tuple notations: Q, sigma, Q naught, capital F, and delta. For example of DFA is here. The given language is W. W is a binary string that contains 0 and 1 as substring. 0 and 1 as substring. If we take any string, it should contain the 0, 1. It should be any place. It is initial state or intermediate or final. But the string should contain the 0, 1. Step for building a DFA to recognize L is first, as we have discussed this DFA is recognized denoted by 5 tuple notation. First, sigma is 0 sigma. That means input symbols. Input symbols are 0, 1. Decide and states Q. Designate start state the final state. Decide on the transitions. This delta function is decides on the transition functions. Q is the number of states and we contain the initial state and final state. Final state equals same as accepting state. We will call as final state as accepting state. Other states, some are non-accepting states. The final state is denoted by 2 circles. Here, see what makes this DFA deterministic. Here there are 3 states. This is the initial state, the intermediate state, this is the final state, and here 1 is self loop and Q0 to Q1 0 transition. Q1 here 0 is again self loop, and Q1 to Q2 is 1, and Q2 is self loop 0 and 1. Like if we want to draw the transition diagram for this regular expression, this is the solution, because here 0 plus 1, 0 plus means here or 0 or 1 star, either it should be empty string or it should be empty string, or it should be a 0 or it should be a 1. And we have discussed that 0, 1 is the substring, and finally last 0 plus 1, it should be empty or it should be 0 or it should be a 1. This is the transition diagram for this regular expression. We will denote this 5 tuple notation Q0, Q1, Q2, and 0, 1, and Q0 is the final state, and if Q2 is the Q0 is the initial state, and if final state is Q2. Transition table here. This is the states. This is the symbols. From Q0 on 0, it goes to Q1. Q0 on 1, it goes to Q0. Q1 on 0, it goes to Q1. Q1 on 1 goes to Q2, and so on. Now, what is non-deterministic finite automata? It occurs non-deterministic implies that the machine is more than one state at the same time. Transition could be non-deterministic. We can easily understand by using one example. This is also, as we discussed, deterministic finite automata is represented by 5 tuple notation. Same here. Also, non-deterministic finite automata is also represented by 5 tuple notation only. Here the same example, but we can represent it in a simple manner. Compared to the DFA, NFA is easy to draw the transition diagram for this regular expression. Here 1, and here 0 and 1 are the self loop. Next to on 0, Q0 on Q1, there is a transition called 0, and Q1 and Q2 there is a transition called 1, and Q2 is the final state, and here the 0 comma 1 are the self loop in the final state. Again we have this, again we have represented 5 tuple notation here, and this is the transition table. Next, what is a dead state? Dead state means if there is in, we will use mainly in the DFA. DFA should contain, every state should contain the, every state should contain the all input symbols. Whenever we don't require the input symbols, so we will simply send it to the dead state. This is the, we will simply call it is as dead state. In DFA we won't use the dead state. This is the difference between DFA and NFA. All transitions are deterministic. Each transition lead to exactly one state. Some transition could be non-deterministic. A transition could lead to a subset of states. For each state transition on all possible symbols, alphabets should be defined. Not all symbol transition need to be defined explicitly. Undefined will go to a dead state. This is just a design convenience, not to be confused with non-deterministic. Accepts input in if the last state is in F. Accept input if one of the last state is in F. Sometimes harder to construct because of the number of states, generally easier than a DFA to construct. Practical implementation is feasible. Practical implementation has to be deterministic, convert to DFA or in the form of parallelism. Thank you.